let's say, topic, which is large generative models. So in this case, one very recent approach, ICLR 2023, that has already an important impact, is Digress, that is based on diffusion models, but it discretizes this process. So in the end, we don't have a probability for the edge, but we have presence or absence of the edge. This is why we call it discrete. So there is a process that is noising, which means we have data. Data is the graph in this case, and we noise it progressively with the model Q. Q is the probability of adding some noise. And we get different versions of the data. So Z1 is the first noisy model, ZT is the last noisy model after T, let's say, repetitions of adding noise. And this obeys to a Markovian structure, a Markovian process. And then we have the denoising process that is trained to invert the noising process by removing appropriately noise between, so starting from the last version ZT and moving to ZT minus 1, removing noise from ZT to arrive to ZT1, and it repeats this several times, several repetitions, and the objective is to reach a denoised version that is as similar as possible to the input data. And at the inference, there is noise sampled from the prior distribution learned, and it is inverted by the denoising network producing some graph. The technical details are very tedious. We don't have the time to go in this, but I suggest that you try to read this paper. In my opinion, it is kind of breakthrough in the area of graph generation, and it is already affecting the current research. So diffusion, this kind of method was not unknown. It has been used in image generation, where we noise and denoise images, and that was the inspiration. So this is the noising process that is discrete. So we have a noising matrix that is given as input. So this is the method that noises this graph GT minus 1, and the result of the noising is GT. It is done through the previous version of the graph and this noising matrix that goes for edges and properties, and so on and so forth. And the denoising phase is a neural network phi theta that is parameterized with the theta parameters, and the denoising process is predicting the P of x and P of e are the probabilities of nodes and edges. So we have this loss function that does the cross entropy between the data and the predicted nodes, and the edges, the real edges, and the predicted edges. Digress is an interesting approach, but it is not very usable in the sense that it cannot be easily prompted. It doesn't have a mechanism that it says generate me a graph with these and that properties. They have their own proprietary way to do that, and so this is difficult to. This is why it is difficult to use it as a baseline in usual experiments where we have known prompts and we want to check if they work or not. So you see here we have the state of the art of graph generators. On molecules, again, see, here we have this QN9 dataset that is larger than the previous ones that we have seen in the previous slides. And we see that the validity of the generated molecules is very high. The uniqueness means that we generate novel molecules. No, sorry, unique means that we don't repeat molecules in the generated dataset. And the training time in the discrete diffusion version is quite fast. What do we have here? Yes, there is also there's an experiment of stochastic block model and planar graphs that need to be, let's say, reconstructed, and we measure validity, uniqueness, and novelty, and you know, they compare the good old graph RNN to the different versions of baselines, and again, digress is performing in almost all metrics better, like this degree, the orbit, but overall it has a big margin of improvement in the case of stochastic block models and in the planar graphs as well. There are more experiments with digress in molecule generation based on the Moses dataset. Now we see for the first time that we have new metrics. We are not only interested in the validity, in the uniqueness and the novelty of the generated molecules, but we have other metrics that are specialized and specific to chemistry, and they have invaded the experimentation, the experimental protocols. And here this arrow indicates if the best value is the largest or the smallest. The same goes for another experiment, the guacamole. And here again we have the validity, uniqueness, novelty, the KL divergence between the distribution of the generated and the real molecules, and this FCT score, I don't recall the exact acronym. And now I would like to present to you a new approach coming from our group that is trying to mimic the LLM approach, but only for graphs. As you will see later, LLMs are still lagging behind in graph generation at different levels. So the architecture that we propose, this is work underway, it is on archive but not published yet. So this is the architecture. So we have a graph and we encode it via some GNN. The representation of the graph, this vector, is going through a diffusion noising process. So we get a noisy version of the encoded graph. And then we have this denoising process that takes into account this noisy vector, but also a vector of properties of the graph. What are these properties? These are the properties that we take into account. These are generic properties, they are not domain dependent. Any graph can be represented by its number of nodes, edges, its density, minimum, maximum degree, assortativity, number of triangles. People that are familiar with the graph mining domain, they will recognize here the important properties that you would like to, let's say, know about the graph. So what we do is that we are, for each of the graphs that we encode here, we have a vector that represents the 15 properties of this graph, the values of the 15 properties that is encoded via an MLP that is concatenated with the noisy version of the graph representation in its repetition of the denoising process. And this concatenation forces the decoder to learn better how to generate graphs with the given properties. Okay, so it's not a huge, leap in architectures, but it's the first time that we, let's say, condition a vector of graph properties together with the graph representation in the denoising process. So beyond that, we built, can I say large? It is 1 million graphs dataset of all kinds, these 17 families of graphs. So we have 1 million of synthetic graphs that are up to 100 nodes. The case of the issue of complexity is quite important here because graphs of 100 nodes require an adjacency matrix of 100 square places, so we cannot deal with very big graphs. So we generate graphs of all these kinds. So we have a very, let's say, representative generic graph dataset, and we train this model with these 1 million graphs, and the resulting neural graph generator model is a small 3.6 million parameters, as opposed to the billions of parameters that we are used from the LLMs. So these are initial experiments, of course, and need to be extended, but the baseline for us was a variational graph autoencoder, and we have two metrics, mean average error and some normalized version of this error. And this is the error that we get in the generation process, comparing variational autoencoder and the neural graph generator. And we see that in most of the cases, the neural graph generator outperforms the variational graph one. And this is the overall, so we see that 55 is the standardized error or null properties for the VGA, and the neural graph generator is 21, significantly better. Then we have other type of testing, which is out of distribution performance. So what does this mean? This generator was trained on graphs up to 100 nodes, but we would like to be able to generate graphs more than 100 nodes. So this is the out of distribution performance. Overall, again, the neural graph generator outperforms the baseline VGA. And we have this masked. So what we do is that we are hiding one property of the graph, and we try to predict it with the generation. And this is the error in the generated graphs for the masking process. The results are less impressive here. So this is an example of generation. So this is the vector of properties of the real graph that we give as condition in the generation process. And this is the vector of the properties of the generated graph. So you see we asked for 15 nodes, and the generated graph has 15 nodes. This is the number of edges. We have an error here. This is the density, if I remember well. So it is the 15 properties. And this is the vector of the real graph and the generated graph for a larger, more dense graph. We did more experiments. We wanted to compare this approach to what LLMs can do, okay? And this is, so LLMs, we see that currently the research community avoids to ask LLMs to generate graphs. The work with graphs and LLMs is mostly asking LLMs whether an input graph has or doesn't have a specific property, if there is a Hamilton path, if it is connected, if there is a path between these two nodes, etc. So we went a bit beyond, and here we have prompts for different models that we tested, including Llama, Mistral, and Gemma by Google. Small versions, apparently, so we can load them in our local computers. And this is the type of prompting that we ended up following many different. I mean, we wanted to be fair to the LLM, so we spent a lot of time developing the best possible prompts so that the LLM does the best possible. And these are the initial results. Work is underway. So what we have here is mean average error, normalized error. So what we do, we have 1,000 samples from the initial test set, and we zero prompted different LLMs to generate the edge list of the graph that we want, based only on the provided graph features. We give all the graph features in a single prompt, and we tested this on this hardware configuration. What we see here is that the neural graph generator that we propose and the variation autoencoder, they are much faster. So you see, the LLMs took between 2 and 12 hours to execute those tasks, whereas the graph retrained models, they took 16 seconds. So this is an impressive speed. So this means that if you want to do graph generation and you don't have enough GPU, or you want to generate a lot of graphs, you need to avoid LLMs. But even the error is optimal here. So this is the kind of experimental evidence that that LLMs are not yet well prepared for graph generation. Specifically, the problem being the execution time. So in the last few minutes, and we have 15 more minutes, I will introduce some efforts that we do in multimodality in the area of graph generation. So graph